Hello and welcome to another edition of Physics 262 Pre-Lecture Tutorials. I'm Dr. Steve Brule. Today's topic is heat transfer mechanisms. First, we'll learn how thermal transfer is measured in either watts or calories per second. Then we'll discover the four things that thermal conduction depends on, and we'll work an example problem. We'll find out what a black body radiator is, and we'll learn the three things that the thermal radiation depends on. We'll work a problem to see why scientists say that human beings radiate about as much heat as a 100-watt light bulb. And finally, we'll explore qualitative aspects of thermal transfer by convection. Well, heat transfer is the exchange of thermal energy between two systems. And here we have two systems. One is fire that's hot, and our hands that are relatively cold. And we've got the three ways that heat can be transferred to our hands. One is by conduction. This should actually be in the fire to illustrate conduction because it's has to be touching both things. And a radiation is the exchange of thermal energy by electromagnetic radiation that goes through the vacuum of space even. And convection is when fluid is heated and then moves to some other place to heat something else and brings its heat with it. Okay. Yeah, I should have said that here. Okay, so conduction happens when they're in contact. All objects at absolute zero radiate energy in the form of electromagnetic waves, and convection takes place when a fluid carries thermal energy from one system to another. Heat transfer is measured in terms of power, which is the heat transfer divided by the time. That is usually measured as, or reported in watts, or 1 joule per second. Could be a calorie per second, which is 4.186 joules per second, or watts. Or a BTU per hour is often used, which is 0.293 watts. Well, first let's look at conduction. Here we have conduction illustrated by an interesting experiment where we have hot water here and cold water here, and we're connecting them with a material that conducts heat from one to the other. The rate at which heat is conducted depends on the difference in temperature. For example, these gloves might be plenty comfortable if the difference in temperature between your hands and the environment was, say your hands are at 35 degrees C and the environment is down at around, let's see, what would be, room temperature is 22, so let's say it's 10 degrees C. They might be all right there, but if you were in a really cold climate, the difference in temperature between the skin temperature and the outside, which might be -10. Well, now the rate of temperature or heat transfer is much higher because the difference in temperature is higher, and we would experience more heat transfer in that case. It depends on the cross-sectional area of the conductor. So here, and I should have told you this a little bit before, here we have a high temperature system and a lower temperature system, and heat is being conducted through this material, which is illustrated by that rod there. And the larger the cross-sectional area of that rod, the more heat that can be conducted from the hot object to the cold object. And this is illustrated by, this is a building that was made in the 70s, and they made windows very small back then to cut down on the amount of conduction loss through the windows to make the area smaller. And it also depends on the thermal conductivity of the conductor. Have you ever noticed that when you sit in a chair that's wooden compared to a chair that's metal, the wooden chair feels warmer than the metal chair? And that's because the metal conducts heat much better than the wood does. And that's the measure of thermal conductivity. And we'll see how that works in a second. And then finally, the thickness of the conductor, how much material does it have to conduct through, the length there, or the thickness. And here we have very thin gloves, and here that's for a warmer area. And look at the gloves on this Polar Explorer are very, very thick to cut down on the heat transfer by conduction. Okay. Well, let's work a problem with conduction. We've got a styrofoam cooler with thickness of 2 centimeters and a total area of 0.8 square centimeters. Yeah, that's right. It is filled with ice water at 0 degrees. The outside temperature is 30 degrees C. Better fix that. What's the rate of heat transfer? Well, we just plug all the numbers in here. We've got K, which was styrofoam, is 0.033 watts per meter degrees Kelvin. That's in Kelvin, so we have to put our temperature in Kelvin. But see, since we're always looking at a difference in temperature in this equation, when we look at the difference in temperature between Celsius, it's the same as the difference in temperature with Kelvin, so it doesn't really matter there. So the difference in temperatures was 30 degrees C because we had 0 to 30. There's the area, there's the thermal conductivity, and this was the thickness of the walls of our styrofoam. And we see that we're losing heat at a rate of 39.6 watts, or 39.6 joules per second. Losing heat. So that means it's really, the heat is coming in from the outside, and there are 39.6 joules of heat that enter our cold water every second from the outside through conduction through this wall. Let's look at radiation. Okay, all objects above absolute zero, and you know what that is from earlier in the course, radiate a black body spectrum. Well, perhaps the most familiar black body radiator is the sun. We all are heated by the sun, and this is the spectrum coming off of the sun, and here is the visible part of the spectrum of wavelengths. Well, you can see where it is. So it starts as the wavelength gets shorter and shorter and shorter. We get to a red here, then we go to yellow, green, orange, and so forth. Yellow, let's see. Roy G. Biv. So red, orange, yellow, green, blue, violet. So that's the order of the visible spectrum, but that's not all of the light that the sun is radiating. Well, it's all the light, but not all the radiation. It's also radiating in the infrared and also in the ultraviolet. So this curve that shows us that the peak radiation is coming in visible light also includes radiation in the ultraviolet, but it starts tailing down here, so we're not getting as much ultraviolet, and it also tails down in the infrared. So it's mainly radiating in the visible, but also radiating some in the infrared. So this is called a black body spectrum because an object, even if it's black, radiates radiation due to this black body radiation. Every object is radiating that's above absolute zero. So it's a black body would absorb all the light that's coming in or any radiation that's coming in because it doesn't reflect anything at all. But then it radiates a radiation according to this black body curve. All right. Here is a metal rod that's been heated up, and it's kind of neat because we can see different colors around here. Right here, it's not as hot as it is right here because we can see that the wavelength that it's peaking at is red in this area, which is a lower temperature than the peak temperature of over here that's yellow. So yellow would be a higher temperature, and if it's blue, man, that is really hot. And over here, even though it's we don't see any visible light coming out of there, we're still getting some infrared radiation. We just can't see it. Okay, let's go to the PHET Colorado EDU site, and we'll see how blackbody curves depend on the temperature. Let's see if I can click that. Okay, here we have the simulation of blackbody curves, and I can give different temperatures of the blackbody radiator, and we see what the blackbody radiation curve looks like. So right there is the temperature of the sun, about 5,800 degrees, something like that, right around there. So that's the temperature of the surface of the sun, and we see that it's the peak radiator, the peak color should be around, oh, it's colder, so it's around in the, it looks like a green, doesn't it? But it should be around in there. All right, so it's looks kind of yellowish, but it's giving all of our colors that we can see. But it's also radiating over here in the ultraviolet and the infrared. So we're still getting a lot of heat from the sun and a lot of ultraviolet, but most of the radiation is coming, or I should say the peak value of radiation is coming from visible light. Well, let's say if we had a cooler radiator, then the curve is going down, and we see that the intensity is going down, but also, so watch that the intensity is going down, but also the peak is shifting to the right. So it's getting to be a longer wavelength as we cool it down. So now here is, I'm just getting to the temperature of a light bulb. And we see that, let me boost this up so we can see its relative shape there. So we see that the peak radiation that is coming from this light bulb at 3000 degrees Kelvin, whose filament is at a temperature of 3000 degrees Kelvin, it's peaking in the infrared. So it's giving out more infrared light than visible. But we made it to do visible, so it's giving out more red than blue here, isn't it? Well, as we lower our temperature, the intensity is going down, but see how the peak is shifting over? It's being even more in the infrared, and we're just tailing off into the visible, and we'll eventually get to a point where we don't have any visible. See that? Let me boost this up again. Just barely, we have some visible. So now it's just glowing red hot. This temperature right here would be red hot, like the poker. And then if we get the temperature lower, now we're not getting any visible light coming off of this object at all, but we still have infrared radiation, but the peak is over to the right. It keeps getting longer wavelengths as we get lower temperature. And see, it doesn't even look like it's 480 degrees Kelvin, which is pretty hot. Looks like there's no radiation. Well, let me boost up my curve here so I can see more intensity, and I'm going to zoom out so I can see longer wavelengths. Oh, let's go back out. No, this way. So it's still radiating, but its peak is over here, and the intensity of the radiation is way, way less than it was when we were looking at the sun. So then we lower the temperature even more. Here's an oven, and then as we go down, the Earth's average temperature, and then even if we got to something that seems like really cold, if we could even go down to liquid nitrogen, it would still be radiating black body radiation. It's just that the peak would be much longer wavelength than something that's a little bit hotter. Okay, let's go back to our normally scheduled programming. Okay, well here we are. It's this is a picture of a cat taken with an infrared camera, and the infrared camera is sensitive to only infrared light, and we can't see infrared light, so it's being portrayed to us using a false color map. So the mapping is as given here. So this is a temperature of 70 degrees, this is 90 degrees. So it looks like the temperature of the eyes are at 93.1. I guess so. So a person, this is Fahrenheit, so a person's body temperature is 98 point something. And so there's the cat's eyes are close to its body temperature, where down here this part of the cat is lower, about 75 degrees, and we can see where the cat has stepped in on the floor. He's heated up the floor a little bit, and made it a little bit hotter than the environment, and that's why that is giving off the infrared light that the environment is not. Okay, the rate at which heat is transferred by radiation depends on four attributes of the radiator. First is temperature, and we've just talked about that. The temperature of the eyes is higher than the temperature over here, so the cat is radiating more heat here than it is here. Surface area. Here, the temperature of this welding arc is higher than the temperature of the surface of the sun, Yet it radiates much less light than the sun because the area is so much smaller than the area of the sun. So the bigger the area, the more radiation you're going to get. Take a look at this picture. Can you tell which rabbit grew up in a hot climate? You should say it's this one. And the reason why its ears are so big is because it wants to get rid of its body heat. It gets hot and it has to radiate that heat somehow. Respiration is only so efficient, so then it's got these huge ears that radiate. A lot of blood flow is coming into the ears, and the ears are warm. And if we took an infrared shot of this bunny, we'd see that its ears are warmer than the fur because it's radiating a lot of heat out of here. Where this rabbit grew up in Alaska, where it was really cold, and it didn't want to radiate any heat, so it grew up with very small ears so it could keep its heat inside its body. And finally, the emissivity of the object. Different objects have different emissivities, and emissivity is the efficiency of the emitter compared to a perfect black body radiation. So a radiator, a black body radiator would emit all radiation that it gets perfectly, whereby if we compare these objects to that of a black body radiator at the same temperature, they're not emitting as efficiently. Although look at human skin here, 98%. Human skin is very close to a black body radiator. Okay. Well, we can calculate the rate of thermal transfer by radiation using this particular equation. And we'll illustrate that with a very engaging problem. Skin temperature of this naked person is 34 degrees. I think I used 35 degrees. Let me make a note to change that. 35 on page 33. People hate when I have these arrows in here. When he's standing in a room at 25 degrees C, the person's skin area is about that. His emissivity is 0.98. What's the net power loss of this person due to radiation of heat? Let's calculate it. So we use Stefan Boltzmann constant there. Emissivity of 98%. There's the area. And temperature to the fourth. Temperature has to be in units of Kelvin. So I add 273 to the skin temperature of the person. And yes, I am using 35. I looked that up. Okay, so that's 750 watts. Wow! Doesn't that seem like a lot? A 100-watt light bulb, feel how hot that is. We're giving out 750 watts, so more than 700-watt light bulbs. But the reason why we don't lose heat at that rate is because the environment is radiating back into us. If we were standing out in space, if we were took off our spacesuit while we're on a spacewalk, we would radiate 750 watts as a black body radiator. But since we're on Earth, where the temperature is 25 degrees, the Earth is radiating back into us. So then our net power loss will be the rate at which the environment is radiating into us, subtracted from the rate at which we are radiating. So our net radiation is 93 watts. And I'll mention that this is not the only mechanism that we lose heat by if we're standing somewhere in the cold. We're also in contact with the air, so we're losing heat by conduction. And as we'll learn in the next section, we're losing heat by convection. There are two types of convection. Convection happens when a fluid carries heat from one system to another. And in this kind of radiator is, or I should say, convection heater is using a natural convection current where the heater is heating these fins and the air naturally rises through that because hot air rises, and then the colder air in the room comes down here and it comes up here. So we get these natural convection currents that form just by heating up this radiator, and the fins take advantage of those. Here's a forced convection example, and that's where we've got a heater down in the basement that's heating the air, and then there's a system that forces the air into the rooms, and then the cold air returns there. So that's a force system that doesn't just happen automatically. You have to have a fan. Your engine in your car has two forced convection mechanisms to efficiently move heat from the engine core to the environment. So here there's a water pump that pumps water through the engine core, whereas if you didn't get rid of that heat, the engine would melt. It gets so hot from all those explosions of the gas. So you have to get rid of the heat. So there's water that is being pumped through the engine block, and then it goes through radiator in your heater if you have that turned on, but mainly it goes through the front radiator. So then the water is going through here, and there's all these little fins to get rid of the heat, but that's not enough. There's a second forced convection current that this fan forces air through these little fins. So then the air, they don't just rely on the natural air flowing like in this natural radiator here. I shouldn't call it a radiator. It's got the fan that's blowing air through there to get the heat out more efficiently. So that's a forced convection mechanism. Here we have an example of a natural convection mechanism where we put a pot of water on a heater, on a stove, and the water is heated, and there are convection currents that form in the water where the hot water rises and the cold water sinks, and that's the most efficient way that the water is heated. If it was just by conduction, it would take a lot longer to heat the water in your pot. It's interesting, I'll just mention to you physics aficionados there, that one of the early experiments in chaos theory was looking at the convection cells that form when you have a pot of water on a stove, and as you turn the stove up and more heat is coming into the bottom, then you first get just 2 convection cells maybe, then they split, now you have 4 convection cells and all that sort of thing in chaos. So that's an example. All right. The insulation we put in our attic and hollow walls is primarily there to prevent convection currents from forming that would, so in your attic you've got all this space in your attic where the ceiling in your house is warm, and then that would heat air, and the air comes up here and brings the heat to your roof, and then the roof cools it and the air comes back down. So what you want to try to do is prevent those currents from forming, and you put some stuff in there. Hopefully it's not flammable. Ideally, you'd fill up this whole area with stuff, but it's too expensive, so we just go to the first few inches there. Well, what did we do today? We learned how thermal transfer is measured in watts or calories per second. We discovered 4 things that make thermal conduction happen. We found out that everything is a black body radiator that's above absolute zero, and there are 3 attributes that affect how much it's radiating. We worked that interesting problem, and we explored qualitative aspects of thermal transfer by convection. Thanks for joining us.